For years, we've been told bigger is better. More parameters, more GPUs, more money. But then a small team in Singapore dropped something nobody saw coming. A brain-inspired model so small it looks like a toy, just 27 million parameters. And yet, it's crushing the giants of AI, outperforming Claude, outsmarting OpenAI, solving problems billion-dollar models couldn't touch, and the strangest part? It learns with almost nothing. No internet-scale training, no endless compute, raw reasoning power. The model is called the Hierarchical Reasoning Model, or HRM. On paper, it looks tiny, just 27 million parameters. To put that in context, GPT-1, the original GPT model from OpenAI back in 2018, had 117 million parameters. That's more than 4 times larger than HRM. Today's frontier models are hundreds of billions, some creeping into the trillion parameter range. And yet somehow, this brain-inspired model is outsmarting giants like Claude 3.7 Sonnet and OpenAI's O3 Mini-High on tasks those systems should, in theory, dominate. So what makes HRM so different? The core idea is that instead of scaling up endlessly and forcing the model to talk its way through problems with chain of thought prompting, HRM mimics something deeper: the brain's structure itself. When you think through a chess game, there's a slow, deliberate part of your brain weighing strategies. At the same time, there's a fast, almost automatic side doing quick calculations, recognizing patterns, and filtering options. HRM recreates that. It has 2 interconnected modules, a high-level planner that works slowly and strategically, and a low-level worker that executes rapid computation. The researchers describe it as a kind of manager-assistant dynamic. The high-level module outlines the plan, the low-level module crunches through the details, and then the high-level updates its strategy. They loop like this until the problem is solved. This back and forth creates what the team calls hierarchical convergence. Instead of converging too early like a traditional recurrent network might, HRM can keep exploring, refining, and backtracking. That's critical for complex reasoning. And the results are jaw-dropping. Take the ARC-AGI benchmark. This is basically an IQ test for AI designed to expose whether a model can generalize abstract rules from just a few examples. Claude 3.7 with 8,000 context scored 21.2%. OpenAI's O3 Mini-High got 34.5, HRM 40.3. And remember, this isn't a giant model with billions of parameters, it's 27 million. It didn't need internet scale pre-training. It learned from just 1,000 examples. Now look at Sudoku. Not the easy Kaggle dataset that most machine learning models can brute force, but Sudoku-Extreme. These puzzles are designed to be tough, even for humans, averaging 22 backtracks per puzzle compared to less than half a backtrack for the common datasets. With 1,000 training examples, HRM hit 74.5% accuracy. The baselines? 0. Claude, O3 Mini-High, DeepSeek R1, they failed completely. Same story with Maze-Hard, a 30 by 30 grid requiring optimal pathfinding. The baseline models failed across the board. 0% accuracy. HRM found the optimal path 55% of the time. And just like with Sudoku, it did it with only 1,000 training examples. For perspective, other teams tried similar maze problems with massive 175 million parameter transformers trained on 1 million examples and barely cracked 20%. That efficiency is part of the magic here. Training HRM to professional level Sudoku took about 2 GPU hours. 2 hours. The ARC-AGI benchmark training ran 50 to 200 GPU hours depending on the setup. Compare that to the months and millions of dollars needed to train a foundation model. We're talking about a system you could train over a weekend on a single GPU, not a warehouse of H100s. So why does it work this way? The short answer? Depth without the baggage. Transformers, no matter how deep you make them, run into vanishing gradients and shallow effective depth. They're stuck in computational classes like AC0 and TC0, which limits their ability to do polynomial time reasoning. Chain of thought was a clever hack, forcing the model to generate text that looks like reasoning, but it's fragile. One mistake in the chain and the answer collapses. And it's slow, token after token, step after step, consuming compute and time. HRM avoids all of that. Its computations happen in latent space, the hidden states of the network, rather than being forced into explicit text. That's closer to how the brain works. Our thoughts aren't just a running inner monologue. Much of the reasoning happens silently, abstractly. Language is a tool for communication, not the substrate of thought itself. HRM taps into that principle. But there's also a practical twist in how it's trained. Backpropagation through time, the standard way to train recurrent models, is memory intensive and biologically implausible. HRM sidesteps it with a one-step gradient approximation inspired by deep equilibrium models. Instead of unrolling every time step, it only backpropagates through the final state. This drops the memory requirement from order of t to order of 1. It also makes the model more stable and easier to train. On top of that, HRM includes deep supervision. After each reasoning segment, it computes a loss, detaches the hidden state, and moves forward. That gives the high-level module frequent feedback, stabilizing training further. And then there's adaptive computation time, ACT for short. This lets the model decide when to stop reasoning. If a problem is easy, it halts early. If it's complex, it loops longer. Think of it as System 1 versus System 2 thinking, fast intuition versus slow deliberation implemented in code. In practice, that means HRM can spend its compute wisely. In Sudoku experiments, the ACT version used far fewer steps on average while still hitting the same accuracy. And if you raise the maximum limit at inference time, the model scales naturally. Train it with mmax equals 8, run it at 16 during inference, and it keeps improving. This is flexible reasoning, not fixed step processing. One concern people always raise is interpretability. With chain of thought, at least you see the reasoning steps in text. But those steps aren't actually what the model is doing internally. They can be misleading. HRM doesn't produce tokenized reasoning, but its hidden states can be decoded and visualized. In maze experiments, you can literally watch it exploring paths, pruning dead ends, and refining the route step by step. In Sudoku, it behaves like a depth-first search, testing numbers, backtracking, trying again. In ARC puzzles, it incrementally adjusts the grid until it stabilizes on a solution. It's not opaque, it's just working in a different medium. And the neuroscientific parallels are fascinating. In the mouse cortex, researchers see a dimensionality hierarchy. Higher order regions operate in higher dimensional spaces than low-level sensory regions. HRM reproduces that after training. The low-level modules' participation ratio was around 30. The high-level modules was nearly 90. Almost a 3-to-1 ratio, mirroring the 2.25 ratio observed in actual brains. In untrained HRMs, this separation disappears. The hierarchy emerges through learning, just like in biology. The implications for real-world applications are massive. Gand Wang, Sapient CEO, has been clear. LLMs are still great for language, creativity, and open-ended chat, but for deterministic, sequential problems, anything requiring deep planning, long-term reasoning, or strict accuracy, an HRM-like architecture is far superior. Think robotics, logistics, system diagnostics, scientific exploration. These are fields where hallucinations aren't acceptable, where compute is limited, and where latency matters. Take robotics. An embodied agent solving a navigation problem doesn't need to narrate its thought process. Token by token, it needs to find the shortest path. Fast. HRM already proved itself in 30 by 30 mazes. Now imagine scaling that into real-world path planning. Or consider healthcare, where data is scarce but accuracy is vital. HRM has already been tested in medical diagnosis tasks and in climate forecasting, where accuracy reportedly hit 97%. That's with small datasets, running on modest hardware. And then there's the economic angle. The scaling race is hitting hard limits. OpenAI's training and inference costs in 2024 were estimated at $7 billion, while losing $5 billion despite premium pricing. Google DeepMind's models require months of training on thousands of specialized chips, and the returns are diminishing. More parameters for marginal gains. HRM blows up that paradigm. It shows that smarter architecture can beat raw scale. For enterprises, the cost savings are obvious. Instead of calling a massive API and paying per token, You could run HRM locally on edge devices or even on a laptop. 2 GPU hours to master Sudoku. 50 to 200 GPU hours for ARC. That's accessible. That's democratizing. Suddenly advanced reasoning isn't locked behind corporate paywalls or geopolitical walls. The code is open source. You can download it today from GitHub and train your own. Of course, HRM isn't alone. There are other architectural experiments underway. Sakana is working on continuous thought machines. BitNet models use single bit weights. Google is testing diffusion-based reasoning systems, but right now, HRM is the one that has broken through. It's not just theory, it's already beating models 4 times its size with no pre-training, no chain of thought supervision, and just a sliver of the compute. And Sapient isn't stopping. They're already working on next-generation models built on HRM principles, with self-correcting mechanisms for broader tasks. Early signs in robotics, control, healthcare, and climate science are promising. The idea is to turn HRM from a specialized puzzle solver into a general-purpose reasoning engine, pushing closer to actual artificial general intelligence. That's all for this one. Thanks for watching, and I'll catch you in the next video.